Okay, let's dive right into this. Engineers have to design some of the most massive, most intricate systems on the entire planet, but how on earth do they even begin to tackle that kind of complexity?
Really think about it. Imagine you're the one in charge of building a whole chemical factory. You can't just, start mixing stuff together and hope for the best. You need a plan, right? A blueprint that can predict how every single part is going to work together, long before you ever pour a foundation or lay down a single pipe.
And that blueprint, well, that's what we call a mathematical model. Now, don't let the name fool you. This isn't just some abstract math problem. It's an incredibly powerful tool that lets engineers simulate reality. It lets them see the future of their design and make sure it all works perfectly on paper before it costs millions of dollars in the real world.
But here's the thing. Creating that model isn't as simple as following one set of instructions. There's not just one right way to do it. Instead, engineers have to make a choice between two fundamentally different paths, two completely different ways of thinking about how to solve a problem.
So, let's call the first path the way of the architect. This is the bottom-up approach. Think of it like this. You start with the smallest, simplest pieces, the digital bricks, if you will, and you meticulously build your entire system from the ground up, making sure you understand every single detail along the way.
So, how does this actually work in practice? Well, imagine you're designing a big water purification plant that uses reverse osmosis. You don't start by trying to model the whole plant. No way. You start with just one filter. You write a couple of simple functions that perfectly describe how that single filter behaves. Then you connect a few of them together. Then you connect a few more. You just scale it piece by piece by piece.
And that's the real magic of the architect's path. If you can get the smallest part right, you can scale it almost infinitely. Your model can grow from one tiny filter to 1,000 of them, from a simple machine to a massive, sprawling factory. There are pretty much no limits to the complexity you can build and control with this method. It's incredible.
But there is another way. Let's call this second path the way of the tool master. Now, instead of building everything yourself from scratch, you find a powerful, pre-built system, some really sophisticated software, and you learn to wield it like an expert. This is the top-down approach.
Now this approach requires a total mental shift. The toolmaster's job isn't to create the functions or build the engine. That engine already exists. It was built by expert mathematicians and programmers. Your job, and this is the tricky part, is to describe your problem so clearly and so correctly that the tool understands exactly what you need it to solve. So, for example, let's say you need to balance a really complex chemical equation. If you're using a tool like Excel's Solver, you don't write the solution yourself. You just set up the problem. You define your variables, in this case, the unknown numbers in the equation. Then you establish the rules, the constraints, like, the law of conservation of mass. And finally, you set a very clear goal. Find the numbers where the mass of the stuff you put in equals the mass of the stuff that comes out. And once you frame the problem perfectly, you basically just hit go. The tool's incredibly powerful. Pre-verified algorithms just take over. They crunch through all the possibilities and spit out the precise answer for you. You're leveraging decades of advanced math and computer science with just the click of a button.
So, okay, we've got these two powerful paths, but here's the reality check about real-world problem solving. It's messy. It's almost never about getting the perfect answer on your first try. The real learning, the real engineering, happens in the process.
This is a philosophy that every great problem solver lives by. Just attempting the problem is a win. Even if you only get part of the way there, you stop and you analyze what worked, and maybe more importantly, what didn't work and why. Because sometimes the most valuable result your model can possibly give you is telling you there is no solution at all.
What does that even mean? You've built this complex model, you've run all the numbers, and it just comes back with nothing. It tells you your problem is impossible to solve as you stated it. Is that a failure?
No, absolutely not. In fact, that can be a massive breakthrough. Take this great story about a student trying to balance a chemical reaction. They set up their model perfectly, but the solver just kept saying no solution. And why? Because their initial chemical equation, the science itself, was fundamentally wrong. And this brilliantly illustrates the point. The model's failure wasn't a bug, it was a diagnostic tool. It proved the students' underlying assumptions were flawed and forced them to go back and find the real mistake.
So, here we are. We have the architect, who builds from the ground up, and we have the toolmaster, who leverages these amazing existing systems. So which path is better? Which one should you choose?
Well, the real answer is it totally depends on the job. The architect's bottom-up path gives you absolute control and a really deep understanding of the mechanics. That's perfect for creating something brand new or for doing deep research. On the other hand, the toolmaster's top-down path gives you incredible speed and access to these powerful algorithms, which makes it ideal for more standard problems or for optimizing something that already exists.
And this is the most crucial point of all. This was never really a choice between one path or the other. The best problem solvers, the truly great engineers, they don't just stick to one way of thinking. They build a toolkit. They master both of these philosophies, and they develop the wisdom to know when to build something from scratch and when it's time to wield a powerful tool. And that is the real art of engineering. And honestly, it's the art of any complex problem solving. It's all about having multiple ways to see the world. So think about the next big challenge you're going to face. Are you going to be an architect and build your solution from the ground up? Or are you going to be a tool master and find the right system to solve it for you? The true expert, after all, knows how to be both.